Resolved semi-analytic model.
All right, hello, can everyone hear me? Okay. So it's great to be back in Santa Cruz. I've been coming to this meeting for a while now, with the exception of last year when I was getting married, but I'm here now. I'm really happy to be back. Neil Katz is kind of a tough act to follow, but I think he perfectly set up this motivation for what I'm working on. So, should we trust simulations? Neil just made the case, maybe not. There are lots of, I don't view this as strongly as Neil does, but I think there are reasons to worry about our current simulations. The resolution you need in the CGM is quite extensive. All of this physics has to be done at a subgrid level. And we're not even sure we have the right physics in the simulations. So one way to do that is to, put everything subgrid. But if you're doing that, why not at least spend some time working on a semi-analytic model? So the advantage of these, of course, is that they're computationally inexpensive. So you can explore the whole parameter space of plausible things. You can test different physics prescriptions, and they're not tied to any particular form of feedback. They're sort of agnostic. They do have disadvantages and kind of a bad reputation, usually 0D, so there's no spatial information. You need to prescribe everything, so you're not likely to be that surprised by the results. And you get a large number of parameters, so they're not great at making predictions historically. But I think part of that is the result of how they were tuned. So usually SAMs are tuned by hand, so it's easy to miss some corner of high-dimensional parameter space. You don't have a good estimate of the uncertainty and the degeneracies in your model, and it's kind of ad hoc. And I don't think I need to convince anyone, given the number of corner plots we've seen so far, that the Bayesian approach is a good way to go, because you can systematically explore the parameter space, you get these uncertainties, and importantly, large numbers of parameters are actually in principle okay, at least. So you can keep on adding parameters, and then at the end, you see which ones are actually degenerate. And there isn't really a huge penalty to doing that. And there are also principled ways to assess different versions of these models. So basically, the philosophy that I'm adopting here is the kitchen sink philosophy. I'm going to put in as much as possible into these models and compare it to as much data as possible. So the particular model that I'm using is one that I started writing here at Santa Cruz. So we take a disk galaxy. We divide it up into logarithmically spaced radial bins, and we assume the disk is thin. Then we solve these equations, which are just the hydro equations in this limit. So we track the gas mass, the stellar mass, the velocity dispersion of both components, the metals in both components, different stellar populations, et cetera, et cetera. The cool thing about this model is that we include these terms which depend on local torques. So the torques are self-consistently moving gas around and heating gas and stars up. And we have different prescriptions for how this torque works. But this is like the main difference between what's going on in our disk compared to what's going on in other comparable models. Just to give you a visceral feel of what these models are doing, I'm showing you here radius versus gas surface density. And these are a whole bunch of, I think, like 100, 400 models with different halo masses. And they're evolving from redshift 4 to redshift 0. And you can see lots of stuff is going on. They're spreading out as more accretion is coming in at the outer edge. Some of them have holes in the center because of star formation and other various processes. So there's a lot going on. So just to summarize here, the input parameters that I'm using, there are quite a few because this is the kitchen sink philosophy. So we have a bunch that control how stuff moves in the disk, a bunch to control the initial conditions, which are at redshift 4 in this case, a bunch to control feedback, and then some to control the accretion process. So this is the model. The data that I'm fitting to are galaxy scaling relations, so usually stellar mass versus something else. And we fit to as much data as we can. So the complete list is here. So we're fitting to as many relations as we can out to redshift 3. And the cases where we can't, it's because the data isn't really available. So we're trying to take a model that has everything and fit it to everything. We're not there yet, but that's the direction. So this is great. One problem, Bayesian computations are pretty expensive. You have to run the model a large number of times. And because I'm fitting scaling relations, I need to run the model a large number of times for each single set of parameters. The model is 5 minutes, so it's cheap, but not that cheap. So this works out to sort of millions of CPU hours, which is doable, but you don't really want to do it. So basically what I did is, the problem is I have these physical variables, and I want to predict observables, and the only way I can do that is run my model. But as the title gives away, I can replace this step with a neural network as long as I give it enough examples. So I take this, so I build a neural network that knows the input physics plus some measure of the accretion history and the halo mass, runs it through a neural network and spits out all these observables. And then this is what I actually use to run the MCMC. So this is also not perfect. The neural network makes errors, and this is like the biggest source of my headaches for the past few years. Anyhow, so assuming it works, we can now run an MCMC simulation. It's approximate because we're using this neural network. And I'm showing here the posterior distributions of all the parameters, the marginal 1D posterior distributions. To read these plots, you see that the green line is the prior and the gray is the posterior. So I don't expect you to read the labels here, but suffice to say, the model is learning something based on the data. So let me show you basically the biggest surprise from this panel. So it's this parameter I call xi. I don't think anyone else uses it, but I recommend that people do. Basically, so when you're setting up a model like this, you need to determine what the wind metallicity is. And there's a minimum value and a maximum value, and xi just interpolates between them. 0 is what people usually assume, which is that the wind metallicity is well mixed with the ISM. And 1 is basically all supernova ejecta are going into the wind and never coming back. So, that's not ideal for enriching galaxies or anything. So that's why my prior is focused towards 0. But it turns out that the model really prefers a pretty large value of this parameter, which was surprising, literally surprising, because this is my real prior. This is what I believed. So the way this model is fitting the results is by having extremely metal-enhanced winds. And as a result, the winds themselves are not that strong. They're weak. So this is the mass loading factor as a function of stellar mass. So the dotted points here are the posterior distribution of my model at different redshifts. And this light blue line here is the results from fire. So these winds are weaker than what people find in some of these simulations, and substantially weaker than what people put into some of these simulations. So since I also want to discuss the Baryon cycle, I thought I'd also mention accretion. This is the wrong caption. So this is another parameter. This is the radius at which gas accretes onto the galaxy. So we assume that at every radius in the galaxy, accretion follows this exponential profile, and it's controlled by this parameter alpha r, which I'm showing here. So as alpha r goes to 0, the accretion is concentrated in the center. As alpha r goes to 1, the accretion is really spread out and basically flat over the course of the galaxy. And so, the canonical value you might expect is about 5% corresponding to lambda, which is down here. But we end up favoring a substantially higher value. So we need accretion to come and settle into the disk with large angular momentum, basically. And this is actually consistent with expectations from simulations. And interestingly, it's inconsistent with the CGM as a mist, as composed of all these tiny particles, tiny gas clouds. So I want to go into a little detail of why I'm making that claim. So there's a lot going on in this diagram, so let's step through it one thing at a time. So this is a rudimentary model of the CGM, basically. On the x-axis here, we have halo mass. On the y-axis, we have various time scales. First time scale is the free fall time. So this is the dynamical time in the halo. Next, we have the cooling time. So there's a cooling time in the hot gas, and we're also assuming that there's a cold phase at 10 to the 4 Kelvin. And these are the cooling times of each of these phases. So you can see the classical result that the cooling time becomes longer than the free fall time around this magical halo mass of 10 to the 12. So to the right of this point is sort of where we expect hot halos to form. So now the question is, in this sort of rudimentary CGM model, what happens if you put in a cloud? So these clouds have a size of 10 to the minus 3, the virial radius. And there are two time scales associated with the cloud. One is the air mass time, one's the crushing time. So the crushing time is the time it takes for the cloud to be shredded hydrodynamically. I think it's really important to note in this regime where you actually have a hot medium, the cooling time of this material is actually extremely short. So I think it's not unreasonable to expect that even though these clouds are going to get shredded hydrodynamically, you're still going to have a lot of cold gas around because it's really easy for it to cool back down. The other maybe more concerning issue is the air mass time. So this is the time it takes the clouds to accelerate. And you can see, if you imagine dropping a cloud in at the outer edge of a halo, for a lot of this parameter space, it's going to slow down substantially before it gets to the center. So why is that a problem? Well, I just told you that we need the accretion to actually occur at larger radii. If it slows down substantially, then all the accretion is going to be concentrated right at the center. So in order to get around this, basically, I think there are two options. Either you need the clouds to be larger than this, which is plausible, fine, or the clouds aren't isolated, which is also fine. We expect them to come in streams. So Doug Lynn and I ran some cute simulations. This is sort of a twist on the classic cloud in a wind tunnel thing. We just had a lot of clouds in a wind tunnel and then blew a wind past them. So you can also sort of think of this as like the transition between a cloud simulation and a stream simulation like we saw yesterday. And what we find is that these clouds in a row protect each other. They increase the acceleration time scale. They slow down the ablation. And you can actually sort of semi-analytically describe this. And so going back to this diagram, that's what these black lines are with different values of delta, which is the separation between the clouds and units of cloud radii. So even with these small clouds, you can easily get them to not slow down. So I think that's it. So the takeaway points are that the program I'm advocating here is that we want to fit everything with a SAM that includes everything. We're not there yet, but that's the direction I want to go. This fitting procedure strongly prefers metal-enhanced winds of modest overall strength. And it also prefers high angular momentum inflows, and that is impossible without large clouds and or collective action of the clouds. So, thanks.
Okay, thank you. If the next speaker could come up. Trying to mix who we hear questions from, so in the back there. Yeah.
So one thing I was slightly confused about, some of these parameters you were discussing, like the wind velocity, wind strength, and angular momentum stuff, those things seem to me, maybe naively, to be mass dependent, but there's just a single parameter that you fit for several decades of halo mass.
Yep.
Is there anything in the code that makes those things sort of become mass dependent, or do you assume that it should be really the same for every,
Yeah.
4 galaxies?
Sure. So for some things where we know a little bit more information, like the mass loading factor, and I'm not just the only one using this parameter, there is explicit mass dependence on the radial properties, the local properties of the disk. For things where I'm the only one using it, like this wind enhancement thing, there is just one parameter, and I'm not sure if that's reasonable. It's probably not. But this is something that it would be easy to test out.
Right here.
So this kind of like related. What was the main constraint that set the parameter about the wind metallicity being so high? I'm just curious.
Yeah. Well, so I can't formally give you an answer to that question since I haven't tried to fit it without different observations. I think that would be a cool experiment. But I mean, I think it's basically the mass metallicity relation. But beyond that, I can't really say.
Because it's very much related to this plot from the Tomlinson et al. Paper that I showed in the introduction of my talk yesterday, that apparently about 80% of the metals you expect to find in galaxies just from the star formation history, the yields aren't there.
Yeah.
So that actually...
Yeah, I mean, the mass metallicity relation is basically telling you the same information. So I mean, just to back up, there's a degeneracy between the raw mass loading factor and how much it's metal enhanced. And you can sort of trade off between those. And this model, when given the option, prefers to put the metals in a weaker wind.
Last question, David.
Right now, your assumption of a completely thin disk as being your only radial component, is it that difficult to add one more component which does not have that assumption, so you can do something like a thicker component or a ball or something like that?
Yeah, I mean, we're evolving the velocity dispersion of these things, and in fact, the stellar velocity dispersions end up being quite high in a lot of cases. And so our formalism for how stuff moves around breaks down a little bit. So we try to stay within a regime where that's not going to be a big problem. But I think, yeah, adding more components to this is something I'm very interested in. Bars, CGM, black holes, add it all.
Okay, thank you. Okay, so our next speaker is Raymond Simons talking about the